Good afternoon, everyone. I'm John Yagachich. I'm the manager of water quality assessment with the Delaware River Basin Commission, and I'm going to present today some of the ways that we use near real-time data to develop interactive data assessments for the Delaware River Basin. So the Delaware River Basin Commission was formed in 1961 with the signing of the Delaware River Basin Compact by the governors of the four watershed states, Delaware, New Jersey, Pennsylvania, and New York, and also signed by President John F. Kennedy representing the federal government. And under that compact, we've got broad responsibility and authority in many areas of water resource management, including water supply, drought management, flood loss reduction, and water quality. We have multiple monitoring programs, but most of those monitoring programs are collecting discrete observations. And so we augment that data with continuous and real-time data, especially that developed by USGS and served up via their NWIS system, and by NOAA served from their port system. And the goal of all of this effort is to turn those measurements into knowledge about the system, so to really better understand the system that we're trying to manage. And today I'll be demonstrating some of the visualizations and products that feed our dashboards that we use for developing and running models, for performing assessments, and some animated plots. And throughout, I'll be talking about what the motivations were for doing this work and some of the tools that we use. So we have a number of dashboards that are updated on a daily basis. These include dashboards for water quality, for flow, for temperature management in the upper part of the basin, and for management of groundwater surface elevations. And you can see the links here to some of those dashboards. And these dashboards really augment the written reports that we develop. And written reports are great, but they all have a common deficiency. And that common deficiency is that they tell us what conditions used to be. And we would really like to know what are the conditions as close to right now as we can get. So one of the products that you see here is a comparison of observed DO to our water quality criteria. And so the scripts behind this pull data from the internet, all from USGS, and compare those observed dissolved oxygen concentrations to our criteria. So the red line that you see there is our criteria value. We would like the DO to be higher than criteria, and that's what we see here, so that's good news. But this also tells us whether the DO is trending up or downward. And so the largest, darkest dot is the most recent observation, and the smaller, lighter dots are the observations in the 5 days prior to that. And what we can see here is that DO is trending downward slightly. And so if we were to look at this dashboard closer to July or August, we would see that these dots would be a lot closer to that line and could potentially drop below the line, which would be a violation of criteria. In addition to DO in milligrams per liter, we look at the percent of dissolved oxygen saturation. So again, these are the same USGS locations. Not all of the USGS water quality meters report out percent of saturation, so we convert the concentration data to percent sat and plot that. And the dark point there, the dark blue dot, is the median value for the day, and the smaller, lighter dots are the individual observations of DO saturation. And when we animate this, we step through day by day through all of 2022. And we see that in the colder months, we're at about 90% of saturation. But as we move into the warmer summer months, we see more productivity, a wider diel swing, and the DO saturation values drop down to near the ballpark of about 50% of saturation. As we get back into the fall, temperatures cool off, and we're back closer to 90% of saturation again. This is a plot of dissolved oxygen data that we've collected by our boat run monitoring program. That's a program that's about 56 years old. And each of the points that you see here is a DO measurement. The blue line is a low S smooth that indicates the structure of that data. And the red line is our criteria. So as we span the time period from 1967 through the current, we see that we go from being below criteria most of the time in the 1970s and early 1980s to being above criteria most of the time closer to the current period. So again, a way of kind of visualizing a very long trend of data in a way that's intuitive and easy to understand. We also have flow dashboards. So the image on the left is a continuous flow profile for one day. So each of the points there is a USGS gauge station, and we knit all of that data together along with tributary inflows to construct that continuous flow profile. That's the blue line. And we plot that against a backdrop of box and whisker plots representing a 20-year period of record. So we can see that for that individual day, in the upper part of the basin, which is on the right-hand side of that plot, we have values that are higher than the 75th percentile, but down at Trenton at the left-hand side, we're within the interquartile range. We also have flow targets at Trenton and Montague, and again, we can see that we're above those flow targets, and that's where we want to be. That's good news. In addition, the animated plot that you see on the right-hand side, that's called an animated choropleth or color-coded map. And so each of the polygons that you see is a Huc 8 subwatershed, and we're pulling data from USGS gauges, and we're computing water yield or flow per drainage area. And we color code that, so when conditions are dry, that's a tan or a brown color, and when conditions are wet, that's a blue or a dark blue color. And so during this time period, in August of 2021, we went from pretty dry conditions, and then we had a couple of rainfall events come through the system and went from dry to pretty wet. There are two parts of the basin where groundwater is managed. So in Pennsylvania, the salmon colored area on the map, that's called the Southeast Pennsylvania Groundwater Protected Area. And in New Jersey, at Critical Area 2. And each of the points on the map is a well that's monitored by USGS. And again, we pull all of the data for all of those wells, and we develop the plots like you see on the right-hand side and feed them up to a dashboard. And so we can see the long-term trend. And the y-axis on that plot is the depth from the ground surface to the water surface. And for this particular well, we see that the groundwater is recharging over that time period. So we're seeing that the distance from the ground to the water is decreasing. And again, under management, that's good. That's what we want to see. So back in 2004, there was a major oil spill in the Delaware Estuary, not the first or the last, but certainly a big one. And in that spill, the Athos 1 ship collided with some items on the bottom and spilled a significant quantity of oil. And at the time that that spill occurred, we had a hydrodynamic model and a water quality model. But the painful lesson that we learned is that if you wait for the spill to occur before you start to model, you're too late. It's just not possible to do all of the work that needs to be done in a meaningful time frame to get the model up and running. So we wanted to try to figure out what parts of this process can we do before any spill has occurred. And what we realized is that we can actually do the hydrodynamic model before any spill happens. And so that is this. What we do is we pull non-tidal boundary data from the Delaware River at Trenton and the Schuylkill River at Philadelphia. We merge together the observed flow along with the predicted flow from NOAA's AHAP system. We also pull the observed and predicted tidal boundary data, the water surface elevation data from NOAA. We knit all of that together into a model input file, and we run that hydrodynamic model, DynHyd 5, overnight every night. Most of the time there is no spill event, and so we don't do anything with the resulting output file from DynHyd. But when there is a spill, we feed that output file forward into our WASP water quality model, and we add information about the spill, and we can predict the location, duration, concentration of the plume, and we can also identify what intakes are likely to be impacted. We can also evaluate prescriptive measures, so we can see if pulsed reservoir release would help flush the system out faster. Now, back when we first put this together in somewhere around 2006, our DynHyd model took several hours to run. Today, we can run that same model in about 10 minutes. And so the pressure for this particular setup is not as great. But we've just completed a multidimensional model, a 3D model, of the Delaware Estuary using EFDC. And because there's so many more computations, that model takes much longer to run. And so we're in the process right now of adapting this system for that same EFDC model. And that will be a tremendous benefit. So we'll be able to have that EFDC model and pretty rapidly develop a water quality model when any spill event occurs. Spills don't only occur in the estuary. In 2018, there was a train derailment at the top of the basin, and a good amount of diesel was spilled. And that led us to understand that we really needed a way to evaluate spill events in the non-tidal part of the basin as well. And so that resulted in this product. What you see in the animated map on the right-hand side, we can identify where the spill occurred in the basin, and we identify the Huck 12 subwatershed. And this tool will compute the flow path from that location to the top of the estuary. So it will figure out where that spill is going to flow through the system. And then for each node in that flow path, it will compute the dilution based on the watershed area to that location. And again, this is all highly date specific. So when we run this, it pulls data from over 300 USGS gauges in the basin, and it does all these computations within about 10 minutes. So within about 10 minutes, we know what the spill path is, we know the dilution at each point in that spill path, and we also identify all of the water intakes that are in that spill path. So we can rapidly reach out and start to communicate that information. Spills aren't the only crisis that we encounter, so we do encounter floods from time to time as well. And we've developed scripts that pull all of that USGS data and develop animated plots of that flood. So this one in 2020 we called the Christmas flood. It happened right around Christmas. And you can see that flood wave develop and move downstream. What's interesting about these kinds of plots is we get some storms that move from south to north, like a nor'easter, and other storms that move from north to south. And so we can see what stations went into flood stage when, and we can get a better sense of how that flood developed in the non-tidal part of the basin. We also get flooding in the estuary as well. And so again, same idea. We can pull the data from NOAA ports, water surface elevation data, and we can animate that flood wave. This estuary flood happened around Halloween of 2021, and we can see that the top dashed line there is the maximum observed water surface elevation for the period of record. And this Halloween flood almost reached that maximum, not quite, just a little bit below it. It's interesting to note that there was no big rainfall event associated with this. This was primarily wind driven. So wind combined with climate change and sea level rise resulted in a very high water surface elevation for that period of time. The dark blue line there is the observed, and the red line is the predicted based on harmonic constituents. So we get a good idea of how much higher the water surface elevation is during this time period than would have been predicted based on harmonic constituents alone. So all of this is made possible through the power of scripted processing. We've developed scripts in R and Python that pull the data, process it, and develop all the plots. Everything that you saw here was done in R, but we've got lots of folks that work in Python as well. And at this point, both of those platforms are pretty equivalent. So if you can do something in one, you can almost certainly do it in the other as well. What we've found is that all of this scripted processing is a bit more work up front, but the return on investment is really pretty tremendous. And so having a script is kind of like having a favorite recipe that you can go back to again and again. So if there was a flood today, or if there was a spill event today, I could simply pull the script from my scripts and run it, and in very short order have a much better understanding in near real time of the condition that we're evaluating. And I'll mention that we're always looking for collaborators. My email address is at the top of the slide here. If you're interested in anything that you saw, or you want to reach out and try and work on something collectively, please send me an email and I'll be happy to hear from you. Thank you so much.